Assalamualaikum warahmatullahi wabarakatuh. And hi everyone. Okay, ladies and gentlemen, welcome to the 63 Distinguished Lecture Series, proudly brought to you by Faculty of Engineering, University Technology Malaysia. So by the way, I am Johanna binti Ahmad from the School of Computing, Faculty of Engineering, University Technology Malaysia. So today I'll be the chair for this session. Okay, before we proceed any further, please feel free to support this event by follow on our Facebook, Faculty of Engineering, UTM. Okay, so today we are very fortunate to have Professor Benoit Baudry all the way from the Stockholm, Sweden. Okay, one of his research focuses on software testing, which is similar to my field. And actually, Prof. Benoit Baudry was my PhD external examiner. Okay, if you have any question for the speaker, please feel free to post it at the comment session. So our admin will assist you for the Q&A session. All right. Okay, so without any further, I will now pass our session to our Dean, Faculty of Engineering, University Technology Malaysia, Professor Dr. Engineer Muhammad Rafiq, to deliver his welcome speech and further introduce our speaker. Over to you, Prof. Thank you.
Thank you, Dr. Johanna. Assalamualaikum warahmatullahi wabarakatuh. Hello, welcome everyone. Welcome to our 63rd UTM Engineering Distinguished Lecture Series. My name is Muhammad Rafiq and I am the Dean of Engineering, University Technology Malaysia. Today, it is my utmost pleasure to welcome Professor Benoit Baudry from KTH Royal Institute of Technology, Sweden. A bit about our distinguished speaker today. Benoit Baudry is a professor in software technology at the KTH Royal Institute of Technology, where he leads the CASTOR Software Research Center. He received his PhD in 2003 from the University of Rennes, France, and was a research scientist at the French Institute for Research in Computer Science and Automation, INRIA, from 2004 to 2017. His research interests include dynamic code analysis, automated software engineering, and software diversification. So that is a brief biography of our distinguished speaker today. Here now is Professor Benoit Baudry from KTH Royal Institute of Technology, Sweden, with his talk on building a robust software supply chain. Professor Benoit Baudry, over to you.
Thank you. Thank you very much for the invitation. Thank you for attending this lecture. So my name is Benoit Baudry. I'm a professor in Sweden, and so today I will talk about something which is called software supply chains. And I will share my screen so that you can see the presentation, entire screen, allow, and then I go there, and then I go there. It works, right?
Yeah, yes, it works, Prof.
Very good. Thank you. So, a brief word about what you see here. So, KTH is a technology university, very similar to the one you are in. It's a technology university here in Stockholm, Sweden, so the capital city of Sweden. It's about 10,000 students in the field of electrical engineering and computer science. And so here I'm a professor in software technology, so it means my research of area is software engineering. And I'm also leading this CASTOR Software Research Center, which is a research center in collaboration between KTH and companies. So here in Sweden, there's a number of companies who do a lot of software and some software research. So there's a number of software companies in the area of entertainment and games. So the big one that you might know about is called Spotify. So Spotify has its headquarters here and lots of software developers here. There's also a number of game studios. And there's another big group of companies who do not necessarily software products, but who have products which embed a lot of software. So in particular, cars, so Volvo, Scania, who builds trucks, Ericsson, who's the largest company in the country, who builds antennas and telecom systems. And so CASTOR is a research center in collaboration with these companies in order to develop software research or software technology research, such as the one I will present today, in collaboration with industry in order to hopefully speed up the adoption of the latest research results in their software development environments. And so the topic I will mention today, I will talk about today, is called software supply chain. Maybe some of you have heard about this before, and so the idea is mostly to introduce you to this concept, introduce you to some of its challenges, and then give a brief word about some research that we're doing in this area. So the key message here is that if you take any piece of software today, be it proprietary software, such as the one you will find in Ericsson antennas or in Huawei antennas or in Toyota cars, or take any piece of software, or this video conferencing system that we're currently using, or the web browser that I'm using to use the conferencing system. Take any piece of software. This piece of software is delivered by an organization, maybe Toyota, maybe Huawei, maybe Ericsson. It's delivered by this organization. It's built by this organization, which means that many software developers within Toyota, within Huawei, within Ericsson code this piece of software. However, when they deliver the piece of software, any piece of software, again, if we take Firefox, which I'm currently using, lots of the code is developed by Mozilla developers, but the Firefox that I'm currently using contains a lot of code built by Mozilla developers, as well as a lot of code developed by other organizations. And this is true for any piece of software. If you take the piece of software running in a car, running in the video conferencing system today, running Skype, lots of code written by Microsoft, as well as lots of code written by other people. And it happens that today, for different reasons, a lot of this other code is open source software. So many companies build software products or build products that embed a big chunk of software. And many of these companies, most of all these companies, reuse open source components as part of their product. So their product is composed of the code they write, the code they maintain, as well as other libraries, other components that they take. And many of these components are open source. The fact that it's open source is not really important for what I'm going to say today. It's just an observation. Many people observe that lots of reuse code is open source software, mostly because open source software has matured enough so that it can be reused. It has matured in terms of quality, in terms of licensing, so that it can be reused in commercial products. And so the key thing here is that this code that comes from elsewhere, it's developed by people who are not part of the organization, is developed following a timeline that is not the timeline of the organization, so not the timeline of Mozilla, not the timeline of Huawei. And it's been developed over the years, and it will evolve independently of the product in which it is embedded. So that's the key point to understand, the key way of developing software today, and it's good for many reasons, and it's also challenging for many different reasons. But that's really the important thing. The important thing is that the bottom line is that today, if you take any software product, open source or not, there is code inside there that is built by the organization who has distributed this product, and there is lots of code that is not built by this organization who has distributed the product. And still inside the product, you will find all this code. So a little bit more in detail, what do I have in mind when I talk about software supply chain and when many people talk about the software supply chain? So if you take one software product, let's take Google Chrome. So if we take Google Chrome, Google Chrome is distributed by Google. And so there are software developers at Google who write some bulk of the code of Google Chrome. And so these developers here in-house, so in-house here is Google. So many developers, they write code, they put this code into something called a version control system. And then every time someone makes a change, this code, the change is put here in this database of version control system and then sent to something which is called a build system. So the build system is in charge every time there is a change in the code base made by an in-house developer. Every time there is a change, the build system will try to rebuild, in this case Google Chrome, in order to check that this new change doesn't break what was working correctly before. So that's the bottom line. The build system runs, the build system tries to, and when I say build includes compiling, includes linking to external libraries, can include testing, static analysis, many different steps which are there to ensure that every time there is a change made by one of those developers, this change does not break, does not introduce a regression. So that's it. If we take Google Chrome, Google developers write a lot of code, develop a lot of code. Every time they develop a new piece of code, a change, new feature, a bug fix, anything, it's pushed here, and then the build system will rebuild the product and then eventually build a binary version of the product, so the binary version of Google Chrome, and that will be shipped to a distribution platform eventually. So that's the way it works in-house. So at Google, at Huawei, at Spotify, at Mozilla, any software company, that's the way they work. The key thing to understand here is that here in the version control system, there's lots of code and there's also configuration files. And there are build scripts here. Those configuration files and those build scripts typically say, okay, in order to build the system, you need to take the code as well as other libraries. So those Google developers, those Huawei developers, those Toyota developers, they write a lot of code, they write very complex systems. However, they don't write everything from scratch. They reuse a lot of code. First thing to think about, they reuse operating systems. Those companies don't maintain their own operating. In very specific case, they do, but let's say that in the case of Google Chrome, for example, they don't have they reuse an operating system. And not only the operating system, but they reuse a database management system. They reuse libraries for encryption, for code analysis, for logging, for many different things. And these libraries, these elements that are reused are declared here in those configuration files and those build scripts. So what does it mean? It means that every time there is a change here, the build system tries to recompile the system. And in order to do this, it fetches the new version of the code from here, but it also fetches libraries from external sources of code. And those external sources of code, they're called package managers. So if we think about reusing an external library, the build system will go and fetch the binary of this external library from a package manager, which is outside the scope of the code that is managed and controlled by in-house software developers. And so those package managers are typically databases that contain binary code for external libraries. think about your favorite npm package, your favorite R package, your favorite Java library. It's there. So in Java, it will be a jar, for example, a jar file. And what's important to understand is that the binaries that are here are themselves pieces of code which have been built and developed by software development teams, which have put the code in a version control system. This code has been built and then eventually pushed to the package manager. And of course, it's more complex than this. So in the build script, you don't only depend from your own code base and one external package manager, but you can depend from many external package managers. So you will include some JavaScript library, you will include some Java library from Maven Central, you will include some Java library from another package manager, etc. And so this whole thing that consists in having different teams build bricks, components, libraries, reusable units of code. So you have external teams that build pieces of code, push these pieces of code in a binary format into some package manager, and then every time you in-house, you rebuild your own system, the build system will also go and fetch code, pick code from external sources. And that's one way to look at the open source software supply chain. I put open source here because it's often open source. It doesn't have to be. What's important to remember here is that the software product that you build here and that you distribute includes code that has been built and configured and controlled by your own software development team, as well as code that comes from external teams on which you have no control, life cycles on which you have no control. Another thing, so that's the first thing to remember. The code here is made of code made by your own people as well as code made by other people. First thing to remember. Second thing to remember, so that's the first thing to remember. The second thing is that there's no other way to do. So it's like this, and there's no other way to do in the sense that your team, your own software development team, cannot do everything. You have to rely on external sources because software systems today are too complex, too rich to be developed entirely from scratch by your own company. So that's the status. Now, what is important here is that, of course, one thing that happens, your teams will introduce bugs in their code, and they will fix it, and that's okay. But of course, external teams will also introduce bugs in their code. These bugs will be pushed as binary format here and eventually end up in your product. So that's one risk. The risk when reusing code, the benefit of reusing code is that it's code that you don't have to build, you don't have to maintain, you don't have to evolve. But of course, this benefit comes at one risk, which is you might have a bug in your product, the product for which you are liable, and this bug is actually coming from an external library. So that's one risk, and that's a risk that people are taking. And the question is, what can we do to mitigate these risks? The other risk, and that's if you read about software supply chain in tech blogs and tech magazines and a little bit in research papers, the other risk is related to security. So one thing that happens is that these libraries that are reused by your product, inside your product, these libraries are developed and maintained by open source communities. One thing that happens is that a malicious user, through different ways, can eventually put inside this code a malicious piece of code, a piece of code that will, if it ends up in your product, it will leak data, it will spy on who is using your product. I mean, any kind of malicious code you can imagine. So one thing is that in these version control systems, a malicious user might put a backdoor, might put a virus, might put malware inside the code. And if it's there, then, and if it's accepted, then it will be put in a binary and then eventually put in your product. For serious open source projects, such as the Apache libraries for Java, or the Linux kernel, or the Bitcoin platform, these version control systems are very much watched, are very much under scrutiny, and it's very hard for anyone to push code here, but it's possible. And there are, we know of times where this has happened. A malicious user, through social engineering, would manage to push some malicious code inside the repo here and then eventually push it there. Another thing that malicious users do to attack the software supply chain is to push libraries which are malicious. So instead of trying to push malicious code inside the code of an existing library, they push brand new libraries that contain malicious code inside the package manager. So of course the question is, why would someone here use a library which is not the one they want, which would use a new library which contains malicious code? So one way of doing this, one attack, is called typo squatting. And typo squatting consists in pushing inside the package manager, inside the trusted package manager, a library which is malicious and which name is almost the same as a legitimate library. So take your favorite JSON serialization library. Let's say it's called JSON, and with a lowercase g, and you push inside this package manager, you push the same library which is called JSON with a uppercase G, or a letter which looks very similar to a G in another alphabet. So that's also a way to do typo squatting, is to use letters which don't have the same UTF-8 encoding, but which visually look very much alike. And this typo squatting, as surprising as it can be, actually has worked, and lots of products have eventually embedded a malicious library that was just because the name was very similar to a legitimate library. And so of course, the risk here is that you eventually end up with a piece of malware inside your product, and then you distribute your product. And as soon as you have the malware and you distribute it to your clients, you suddenly distribute millions of copies, and this is how the malware can spread. So the software supply chain is necessary. So as I mentioned earlier, there's no way to do otherwise. You have to rely on external software, because you cannot rebuild everything from scratch in any domain, be it the financial domain, the entertainment domain, the energy domain. Healthcare is also a big thing. Transportation is a big sector with lots of software that relies a lot on external open source software. And of course, the web-based applications, you have to rely on external libraries, but it's also important to realize that it's a risk, and that today some people in companies as well as in research labs are building technology in order to mitigate these risks. So that was the main message here. The main message is that there is something called the software supply chain. The software supply chain is all this software that is needed in order to, is all this software and all this software that is needed to build the libraries that you put in your own product. And so there are the libraries themselves. There's the package manager, which is itself a software platform. There's the version control system, there's the build system. All these systems are software at different levels, and all of these can be potentially either contain a bug or be attacked. And this will eventually introduce an issue inside your product, even though your team did not introduce this problem. this is the way it is, and so the question is what can we do to mitigate this? One thing that a lot of people look at this from the perspective of the open source or the software ecosystem on which you rely. So one big issue, which is not, at least is not completely, is not only software technology, but it's a big issue in terms of liability and in terms of business, is licenses. So typically those libraries, they don't have the same license, they don't have the same rights. And so there's a big question at the end when you distribute a product that contains lots of code, every line has a license. Some of it is your own internal code, so this is fine. And some of it is external code. And the question is, are these licenses compatible with each other as well as with the business model that you have in mind? And that's a big thing. Another way to look at the ecosystem is to look at when you reuse a library, when you reuse a package, who is building it? How often is it fixed? How big is the community of developers? How easy is it to make a change? How many people are in charge? This is called the truck factor. So the truck factor is how many people would it take to kill somehow the library. So how many developers are in charge? If it's a small number of developers, then you have a high risk, because if something happens to this developer, then suddenly the package that you reuse is not maintained anymore, is not updated anymore. So you have a number of metrics which are about the way the code is developed, the way this external code is developed, more than the code itself. There's another, so that's understand the open source ecosystem. Another way of looking at this is to secure the development pipeline. So as I mentioned earlier, everything starts from one developer making a change in the code somewhere, and then this change in the code is passed to a version control system, and then it's passed to a build system, to a compiler, is pushed onto a package manager, a deployment platform. And so all along the line, the question is, how are we sure that the binary we get has not been tampered with? So how do we ensure that the binary we get contains no more and no less than the code that has been pushed by the developers? And so there's a number of lines of research along how to sign commits. So the person who pushes a change has to sign with some cryptographic keys. How to have reproducible builds. So how to ensure that if I take a piece of code and I build it, I get this binary. And if I do it twice, I get exactly the same binary, the same SHA, the same hash code for the binary. And that's, again, a whole very complex line of research. Very few people today do reproducible builds. In the open source world, the most famous ones are Ubuntu and Tor, and the Bitcoin Foundation. They have a very strict process to build their binary so that they can ensure that the binary they build is the result of changes in their source code. And the last point I want to mention, so you can look at this from an ecosystem perspective, and so licenses and developers. So what's the social, economical, so the social technical network of people, how does it work and how is it maintained? You can also look at the pipeline and how to make it more secure. And there's one line of research in which we are more interested in, which is called dependency management. And so for this, I will refer you to this very good paper, which is a very good summary of what it takes to manage software dependencies today. The paper is called Surviving Software Dependencies. It's been written by someone who builds the package manager for Go. And he identifies several challenges and several ways to take care of your software dependencies. So one of them is to inspect them. So this is related to metrics I mentioned before. Given one external library, how often is it updated? How often is it maintained? How many people maintain it? Test it. So it's not because you reuse a piece of code that you should assume it's correct. Abstract it. So that's something a bit more technical. Here is when you depend on an external library. The idea here is to add a layer of abstraction between your code and this external library so that if you need to change this one, you don't need to change your code too much. So to reduce the coupling between your code and this external library. It's also related to this idea of isolating from the external libraries. One thing that I will talk a bit more in detail about is avoid external libraries. So in many cases, it's very easy today to reuse external code, which is good because reuse is good. So software reuse is a good thing. And today, many people have worked very hard to facilitate software reuse. However, today we see the counterpart of this, which is people tend to integrate in their products more libraries than is actually needed. So one advice is to avoid using libraries which you don't need. It's not to avoid reusing. Reuse is good, but reuse what you need, not more. And of course, and the last one is upgrade, which is a very generic guideline in terms of security, which is valid here for software dependencies, which is valid for any product that you have. Is upgrade is always a good idea. Get the latest version. So dependency watch and upgrade. One thing is when it comes to upgrade, it's so important that you might have seen this. There are bots. So there are programs which are in charge of looking at your code, looking at your external dependencies, and check if your external dependencies are up to date. And they will send you a warning in the form of a pull request, for example, if you don't have the latest version of the dependencies. So one of these bots is called Dependabot. You might have seen it if you have code on GitHub. So GitHub acquired an external company 2 years ago. And this external company builds something which is called Dependabot. And Dependabot automatically screens all GitHub repos in Java and JavaScript. I think it's only for these two languages today. They screen all the millions of GitHub repos that have Java and JavaScript code. And what they do is that they look at their dependencies. So they find the external dependencies and they compare the external dependencies of each repo with an external database of vulnerabilities. And they say, okay, if your repo contains one dependency which has a known vulnerability, then I will let you know. And I will ask you to upgrade your dependency. This is Dependabot, which is today in GitHub. Another bot, very similar and also very good, is called Renovate. And Renovate is open source. You can look at the repo here. It is multi-language, so it works with more than Java and JavaScript. And it sends automatic pull requests. Same thing. It has its own database of vulnerabilities, and it will warn you if you have not upgraded your dependencies. And so, as I mentioned earlier, the last point I want to mention is a little bit of detail about how to avoid dependencies, which might seem a bit surprising because, again, I insist, reusing external dependencies is necessary. It's impossible to not do it. Today, there's no serious company who would try to build a serious software product without relying on external sources of code. We cannot, things are too complex to do everything from scratch. So we have to depend on external libraries. However, we should not depend on more libraries than we actually need. And so the idea here is that if we look at a piece of code, if we look at a software product, we will find code that is provided by external organizations, external dependencies, and sometimes inside the code base, we find external dependencies which are actually not used by the software product. So you build your product, Google Chrome, and you, software developer of Google Chrome, you say, I need this external library. I need this advanced logging library for this specific feature. And so you say, okay, I depend on logging library. What does that mean? When you build Google Chrome and you say, I need to depend on logging library, the build system, what it does is that it takes the code of Chrome, and then it fetches the logging library and it puts everything into the binary. So it means that at the end, the binary of Google Chrome contains your code as well as the code of the logging library. So the code is there, and if there is a bug or if there's a vulnerability, a piece of malware in the logging library, potentially this can trigger a problem. However, it happens that sometimes when we look at the code here of Google Chrome, we realize that the logging library is actually never used. So this piece of code could be removed from the binary product, and the Google Chrome would work as well. And so avoid dependencies is really this, is how can we automatically detect that some dependencies which are put inside the binary product, inside the software product, are actually not needed and can be discarded, can be removed, to facilitate dependency management, to facilitate updates, because of course a library that you don't have anymore among your dependencies is a library that you don't need to upgrade, is a library for which you don't need to care, is a library that will not bring malware, etc. And so this is the very focused research area that we have in my group in this big topic of software dependencies. So how can we automatically detect unused, we call them bloated software dependencies? So we have built a tool which is called DepClean. It's open source, it's for Java only, and it will automatically detect bloated dependencies in a Java project. So let me illustrate this with an example. So this is an example of one open source product, which is called Spoon. So Spoon is itself a library that does code manipulation. So the code of Spoon is here. And what we see here is that this is the code maintained and developed by the Spoon development team. And when the Spoon product is built, this code is taken as well as all the many dependencies. So what we see is that the Spoon development team said, we reuse external libraries. And so the libraries which are directly declared by the Spoon development team are here in this first ring in the graph. And what we see is that, of course, when the Spoon development team says, I depend on this library, well, the development team of this library also said, I depend on other libraries. So for a given project, we have the code built by the project development team. We have the code of the dependencies declared by the project development team. And we have the dependencies of the dependencies, so the transitive dependencies. So for this example, Spoon has its own code base and it depends on 75 dependencies. Talking about the software supply chain, here we have put colors. So each color corresponds to a different organization. So each node is a package of code between 50,000 and 500,000 lines of code. So each node in this graph is a chunk of code. And each color corresponds to one organization. It doesn't matter which one. What matters is that there's lots of colors. So it means that the Spoon development team builds its own code and relies on many other code to build its product. And these other pieces of code are built by many different organizations, many different teams. Here we have 24 different providers. So 79 dependencies, 79 chunks of code more or less big, provided by 24 different organizations, who can be in Asia, who can be in America, in Europe, very international, very national, very big, very small. It can be anything. What matters is that at the end, the binary thing distributed by the Spoon team will include all of this code, their own code, as well as all of this code. Now, if we look a bit more carefully, first, Spoon uses something called Maven as the build system, and Maven will remove some redundancy in the dependency tree. So this is the complete dependency tree, and here in gray, we have shaded, we have almost removed some dependencies which are excluded by Maven. And then we run dep clean. So dep clean is our own tool, and so dep clean will perform some static code analysis, and we'll look at automatically read all of this code and tell you, okay, look, Spoon development team, you say that you depend on this library, and that's true, you depend on it. Your code here needs some code that is here. However, remember that this code here, maybe it's 100,000 lines of code, and you reuse a part of this code, but not all of it. And actually, you don't reuse the part of this code that itself depends on these other libraries. So this piece of code declares dependencies, which are transitive from the point of view of Spoon. But to build Spoon, we need a part of this code, but we don't need the part of this code that relies on these transitive dependencies. So it means that we can remove those dependencies. And so at the end, starting from 79 dependencies in the dependency tree of Spoon, we can reduce it, thanks to Maven and dep clean, we can reduce it to the parts which are in blue here, which is a tree that is much smaller than the initial one. And so that's how we can avoid embedding external libraries. As to illustrate what it means on non-open source code, we have a partnership here with Ericsson, and they have used our dep clean tool on some of their code bases, and they have found similar results. So they have found some, in orange here are the number of dependencies which are not necessary, which are bloated, direct dependencies, so directly declared by the Ericsson developers, as well as transitive dependencies. In some small projects, they have found very little bloat, but in larger projects, they have found a lot of bloated dependencies. So this hints on the fact that there is a real benefit at running this kind of analysis in order to remove dependencies which are not needed. Because you have to rely on a complex software supply chain. But what we know today is that a part of this software supply chain is supplying software that is actually not needed. So we take more risks. These companies take more risks than actually needed. So as a conclusion, the software supply chain is this concept, the fact that inside a code, any organization that builds a software product deploys, distributes code that they have built as well as code that they have not built, and they distribute the whole package. This is necessary, but this is also a risk for dependability and security. And today there are many different solutions, going from analyzing licenses and the socio-technical network of people who build those external libraries to more tool-oriented technical solutions that will run automatic analysis on the dependencies and help you reduce the surface of the software supply chain. And this concludes the presentation, and I would be very happy to take questions if you have some.
Okay, thank you very much, Professor Benoit Baudry. It's a very interesting topic. And we can see that we have about 120 audience that watching our webinar today. Okay, so I think there are a few questions from the audience. All right, the first question, Prof. Can you read the question, Prof?
Yeah. So if the package manager contains any error, will it affect the inner build script? So yes, that's a challenge. So in the open source world, the very well-known package managers, which are heavily used, for example, to build web technology, npm for JavaScript, PyPy for Python. So if you do data analysis, data management, you will use lots of Python code, machine learning Python code, and Maven Central for Java. Those are three big package managers, and they are constantly updated. They are constantly scrutinized. The teams are very, very careful because they know, and there has been examples in the past of bugs inside the package manager, which actually lead to problems in applications that depend on these package managers. So yes, it will affect the inner build.
Okay, this is the second question. I think the third-party software refer to the open source.
Yes, exactly. So this is true. So people reuse external libraries, trusting these libraries. So one way to do this is to use external libraries built by trusted parties. So for example, the Linux Foundation, the Linux Open Source Foundation has some packages like the Linux kernel, or the Apache Software Foundation has a lot of Java packages. And these foundations curate the packages they distribute. So if you reuse a library from the Apache Foundation, it doesn't mean that you should be completely blind, but it means that the level of trust that you can put in these packages is higher than any random package that you find on GitHub. So that's one way people deal with it, is that they reuse external open source libraries from trusted parties. And how do you build this trust? Well, you build it because these people are serious, because they have transparent guidelines on how they take care, they curate their code. So that's one way. And the other way is that it's always good to rerun. So when you take the open source package, you can take it directly from those package managers, but you can also take the source code. If it's open source, then you can take the source code and rebuild it, recompile with your own compiler, test it with your own testing environment, and this will increase the trust. And so, for example, at Ericsson, this is what they do. They never reuse a binary coming from a package manager. They take the source code and they rebuild it inside their own pipelines of build. And they run their tests and they run the static analysis tests, etc.
Okay, so this is the third question.
Is it okay if I use open source code and I decode it to fix bugs? Not completely sure I get the question, but so the one part of the answer is yes, it's okay to reuse open source code. I strongly encourage you to do it. And yes, it's very much okay to report a bug if you find one. So if you download an open source package from an open source platform such as GitHub or GitLab, you use it, you test it, and you find a bug, this is a very good practice to report this bug and maybe even report the bug fix. And so for this, you have something which is called a pull request. So a pull request is a way to contribute back to the open source package if you have found a bug and if you have found a fix.
Okay. So the next question is about the task allocation.
Yes. Thank you for this question. I'm not completely sure what you mean by task allocation.
Maybe when they work in a team, I think so. Because we involve the third party is maybe from the open source, and then maybe from the Ericsson itself, the software development team, which is different. They are from the different organization.
Yes. So if task allocation in this case means that the different parts of the code have different timelines. So there is the timeline of your in-house organization. So your developers build code, and then there's the timeline of the external library. And so the developers of this third-party library have a different timeline.
Okay.
There's not much to do. So you as a developer of your own product, the choice you have is when do you upgrade, when you decide to change the version of the library on which you depend. That's one thing you have control over. So today you use the logging library version 1.4.2. There is a version 1.5. So it's a major release that came out. And the question for you as a developer is, do you upgrade? A good reason to upgrade is that this version 1.5 probably fixes some bugs of version 1.4.2. But it might also introduce some new bugs or some new problems, or it might not be fully compatible with the previous version. So you have a choice to make. When do you upgrade? And so that's typically a fully distributed. Of course, there's no central decision system here. So what people do, so there are the early adopters. So there's always people who will upgrade, immediately want to get the latest version to test if things are okay, because they believe that it's good to have the latest version, because maybe they have build systems that automatically go to the latest version. And then there's a long tail of later adopters. And those later adopters, the strategy they have is usually they look at the early adopters and they say, okay, if there's no problem for them, then I will go for it. So usually there's a lag. So there are people who go to the latest version as soon as it comes out. And then there are the later adopters who will go there only if the early adopters haven't found a major problem. I'm not sure this is what you meant, but that's one thing.
Okay, next question is from
okay, so again, I don't have a complete perspective on this question. So everybody can see the questions, right? We don't need to read them.
Yes, everybody can see the question, Prof.
Okay. So there are several ways to look at this. So one way to contribute to an open, so there's one first thing to do to contribute to an open source project is to have access to the open source repo. And so we know, so one big platform for open source software is called GitHub. And GitHub has been acquired by Microsoft 2 years ago, which is good and bad. The good thing is that Microsoft puts a lot of money in it, so GitHub becomes stronger. But the bad thing is that GitHub also became closer to governmental agencies, let's say. And so we know that GitHub has started banning users from specific countries. And so that's the main issue, because if you cannot have an account, if you cannot log into GitHub, then there's no way you can contribute. And so that's a big thing. It's a big battle, and it's way beyond technical questions. It's very political. But so that's one thing. You first need a GitHub account. Then if you have an account, as far as I know, you can contribute to open source projects. And in particular, for example, if we think Apache Foundation, the Apache Foundation does not forbid contributions from outside. There are some other foundations, open source foundations, that are a bit less vague about how they accept contributions from outside. And in any case, if you are from anywhere in the world, if you want to contribute, you cannot contribute directly code. So the way you do it is that you propose code through a pull request, and then this code is reviewed for its quality, for its relevance to the project, and then eventually according to its provenance. And this is where and things change very fast, as you know better than me, I think, the world is moving very, very fast, and in particular, we have heard stories of people who are not allowed to contribute, and yeah, that's happening. I know it's happening.
Okay, next question, Prof.
Did the robustness of the software supply chain depend more to the practical implications in companies? Again, not completely sure. I will get the precise question. So one part of the answer here is if we take the companies we work with here in Stockholm.
Mm-hmm.
Some of them have, so these companies, as I said earlier, they build a product. Inside the product, so they build a product and they sell a product, a software product. Inside this product, there's code that they have built, and this code comes from third-party libraries.
Mm-hmm.
When they sell this product to a customer, so if we take the example of Ericsson, they will sell their products to AT&T in the USA or British Telecom in the United Kingdom. These customers sometimes impose some requirements on the software supply chain. So the customers, it's part of the contract that Ericsson signs with their customer. Inside the contract, very, very big contracts, hundreds of pages, and some pages are about some practices for the software supply chain. So some customers will require to not have code coming from Apache Foundation for whatever reason. They will require to remove unnecessary dependencies. And so this is where practical implications, that's how I understand it, or at least this is something I've heard, is that one practical implication is that the company that sells the software product inside which there are dependencies signs a contract with a customer. And sometimes in this contract, there is an explicit mention about how to manage the software supply chain.
Okay. Next question. Can supply chain software tackle the risk of supply disruption due to COVID-19?
So there are several risks. That's what I mentioned earlier when I said analyze the software ecosystem. So some people look at this, and so one way to mitigate the risk of COVID is to first of all use libraries which have several main contributors instead of one. So if you use a library that is very good, very robust, but that is maintained by one single person, it's a big risk because this person can be sick, this person can die. But anyway, so one way is to rely on libraries which are maintained by several people. Ideally, those people are in several different locations. And then, of course, with COVID, we also know that the teams which maintain the infrastructure, so which maintain the package managers, which maintain GitHub, the online version control systems, these teams are a bit more fragile. And so there's also a risk that these services are not available. But so theoretically, there is a risk. In practice, one way to mitigate the risk is to use libraries which are maintained by a group of people instead of a single one.
Mm-hmm. Okay. No question? Okay. I think there are no more questions, Prof. Okay.
Very good.
Thank you so much. I'm
Thank
glad
you.
to see you virtually. Okay, so with that, I will pass on our session to Prof. Dr. Muhammad Rafiq for closing remarks.
Thank you, Johanna, for chairing the session today. And to our invited speaker today, Professor Benoit Baudry, thank you so much for your very interesting lecture. And thank you also for accepting our invitation to speak at our distinguished lecture series. And to all of you watching this webinar, do stay tuned because we have many more lectures for you. Until then, bye-bye for now. Bye-bye.
Bye-bye. Thank you very much.
Thank
Bye-bye.
you.
Much.